This is the last week of the 12th week of the Applied Thermodynamics course. So this week we will see about compressors. So previously we saw the power cycles and energy. We did energy and energy analysis of all systems. We saw Rankine cycle and other type of cycle. So compressor is basically is one of the components majorly used, and we'll see how some numericals on those. So compressor basically can be of two types. You have one positive displacement and the other is a centrifugal or rotary type. So this positive displacement can again be of two types, can be a reciprocating or a rotary. So this rotary type of positive displacement will be a lobe type or a screw type kind of compressors, or a scroll type, and these are just two rotating screws of in-depth screw types will come together and it'll compress the air which is going in the casing and the screw in between. And similarly in a reciprocating, it's just another piston type compressor that is used. And if you see there's a dynamic, and there you have a centrifugal compressor. There you know where your kinetic energy is used to increase the pressure. So your fluid which is coming in, it's thrown out to again the impeller with the centrifugal force. So there is an increase in velocity, and then when it comes out to the volute, the kinetic energy is converted back to pressure energy. So that's what happens in a dynamic or a centrifugal type compressors. So these are the majorly the different types of compressors available, and if you see a different between these is in a reciprocating compressor, it's not continuous. You have a gap between each. There's an intake, it's compression, and then exhaust. So and then it should take an intake. So it's not continuous if you compare it to centrifugal. So there is a distinct difference there, and it's also the compressor selection depends upon your flow rate and your pressure ratios which it's required. So generally for higher pressure ratios, you generally go with a reciprocating type, and if you have a larger volume which you require, then you go for a centrifugal type compressor. And this other rotary type positive displacement will lie somewhere in between. And sorry, so this is the general idea of how compressor works. And so we'll see some numericals on in some MCQs starting with, and then we'll go on to solve some numericals, basically majorly on reciprocating type compressors, because if you go for a dynamic, then you have to do a velocity diagram and you have to study based on the angles. So this compressors will start with just a thermodynamic analysis, and in some case we'll design a reciprocating type compressors. So starting with the first question is rotary air compressors are suitable for dash. So higher discharge at higher pressure, low discharge at high pressure, higher discharge at low pressure, then low discharge at low pressure. It's just the discharge and pressure. The pressure is generally the pressure ratios. If a higher pressure ratio, then your exhaust pressure is basically more. So just now I told this. So rotary air compressors is used when you have a larger volume. So it's option C, higher discharge and low pressure. So the next question is reciprocating air compressor is positive displacement machine. So is this being a true or false question? So we know this is a positive displacement machine. So reciprocating is a positive. You have this and other. Basically, I listed out the two differences: positive and dynamic. So reciprocating will fall under positive displacement machine. So this statement is true. The next is, in an ideal reciprocating air compressor, the work input will be minimum if the compression follows a dash. So ideally reciprocating the minimum work input. So you have listed out 4 processes. So you have reversible adiabatic, that is isentropic process. Then you have an isobaric process, and C adiabatic process, and D isothermal process. So isobaric compression, it's then your pressure is remaining same, so it doesn't make sense. Even then, if you take, then P will be P into delta V, that will have a larger work done. And if you see the other 3, if you is just to find out the curve between the if you draw all the process in a PV diagram, so the process which occupies the least amount of work under its curve will have the least work. So in that sense, the isothermal process will be the one which will have the minimum work under the curve. If you draw the processes, maybe I'll add that if diagrams of all the processes here when I upload the PPT. So if you see there, the isothermal process will come first, and then the next one will have, you have reversible adiabatic process, adiabatic or an polytropic process, and then you will have a reversible adiabatic. For that, gamma will be 1.4%, and then you have isobaric. Isobaric will be straight line. So your minimum work will be for the isothermal process, and you can calculate that RT1 ln P2 by P1, your pressure ratios. So that will be your work done. And for other adiabatic or isentropic process, similarly, you have to just integrate V delta P. So moving on, for a reciprocating compressor, as the value of pressure ratio increases, the volumetric efficiency dash. So in a reciprocating compressor, if your pressure ratio is more, so what happens to volumetric efficiency? So this is actually it will decrease, and you have a relation for this, but if you see it physically, what happens physically, and why does the volumetric efficiency be more? So if you take a practical compressor, reciprocating or the piston type compressor, so it's working at some pressure ratios. So you have some clearance volume that is required because you have valves and also seat. So based on the construction feature, you require some clearance volume to be there. So when you compress the air or any fluid inside, and you compress, the pressure is at the higher pressure, discharge pressure, which you want. So your valve opens, and the fluid which is there, it will go out. And because of this valves and the arrangement, the fluid which is there will all not go out, but some amount of fluid will be present in the compressor. So what happens is now is when the piston goes back, so this will expand. So when this expands, and this the suction valve will only open when this pressure is lower than the suction pressure. So the valve opens and the fluid comes in. So when what happens is, if you go for higher pressure ratios, the fluid which was remaining after the exhaust, the discharge pressure which the fluid left, so that will be at higher pressure. And what happens is, when the piston moves down, it will take larger volume for the pressure fluid inside the compressor before suction. It will take a larger volume for the suction stroke to reach the suction pressure. So what happens is, you will have very small volume left for to take in new fluid. So if this happens, your volumetric efficiency is nothing but mass of fluid which is coming in divided by the swept volume mass, or you can take the volume of fluid coming in by the swept volume. So the volume of fluid coming in has gone down because a larger volume was already taken by the fluid which was there in the compressor. So this is what actually you can think it of physically. So the volumetric efficiency will go down, will decrease it, and the formula will same the same thing, 1 minus C plus 1 plus RP raised to 1 by gamma. So if you think in that point also, if the pressure ratio goes up, there's a negative sign. So your volumetric efficiency will go down. So the next question is, I hope the previous explanation was clear. If you have any query, you can ask anytime. So the next question is, in perfect intercooling arrangement in a reciprocating compressor, it is possible to achieve the isothermal compression with minimal work input. So if in perfect intercooling, perfect intercooling happens when you reach the temperature after intercooling, it's equal to the suction temperature at the first stage. So that's what perfect intercooling means. So it is possible to achieve isothermal compression with minimal work input. So this statement is true. So we'll see some numericals on your multi-stage compression. So basically what you are doing is doing an intercooling, you are trying to approach the isothermal process. So if you see isothermal process, what happens is you have compression. During that you are putting in work but also rejecting heat. So if without rejecting heat, you cannot maintain the temperature constant. So because you are putting in work, your fluid temperature will go up. So to reduce the temperature, you have to dump some heat to the atmosphere. So this has to both has to take place simultaneously, which is very difficult to achieve. So that's why we normally go with a polytropic or an adiabatic process assumption, because our compressors are very fast. You have very less time for heat transfer to also to happen. So here with doing an intercooling, doing a multi-stage with an intercooling, what you are trying to achieve is you are trying to go towards an isothermal process. So hence the statement is true. So the next question is, in a two-stage reciprocating air compressor with a suction pressure of 4 bar and a delivery pressure of 16 bar, the ideal pressure for intercooling will be, so this will be 8. So we know for intercooling the ideal pressure is root of P1 by P2, the lower pressure and the higher pressure. So root of this you can get it by writing the total work done, and you can differentiate with respect to the intermediate pressure. So you can find out this relation there. So for intercooling, the intermediate pressure will be root of P1 into P2. So your P1 is 4 bar and P2 is 16 bar. So root of 4 into 16 is 64, that is 8 bar. The next question is, the ratio of the volume of free air delivery per stroke to the swept volume of the piston is known as. So this just now I explained what this is. It's a volumetric efficiency. So volumetric efficiency is, you can write it in terms of mass or it can write it in terms of volume. So here it's volume of free air, the air which is delivered, divided by the swept volume of the piston. So that's volumetric efficiency. So the next question is, an air compressor receives in air at 1 bar and 20 degrees Celsius. So this is your inlet condition at 1 bar and 20 degrees Celsius, and compresses it according to law PV raised to power 1.2 equals constant. So it delivers the air to a receiver at constant pressure of 10 bar. So your discharge pressure is 10 bar. The temperature of air at the end of compression is, so you have to find out the temperature at the end of compression. So we know inlet temperature. So inlet temperature is 20 degrees, which is 293 Kelvin, and we know pressure, inlet pressure or suction pressure, which is 1 bar, and we also know the discharge pressure, which is 10 bar. So we have to put it into the receiver, which is at 10 bar. So discharge pressure is 10 bar. So now your the process which is happening is governed by the PV raised to power 1.2 equals C relation. So uh, we find out PV raised to the pressure and temperature relation. You can substitute ideal gas equation PV equal RT and into velocity. You can into volume, and you can find out the temperature and pressure relation. So it will come out to be T2 by T1 equals P2 by P1 raised to power n minus 1 by n. Here n is 1.2. So we know the pressures, so we can find out pressure ratio. Pressure ratio will be 10, and 10 raised to power 0.2 by 1.2, which is 1.468. So your discharge temperature is nothing but your inlet temperature into 1.468, which will come out to be 430 Kelvin or 157 degrees Celsius. So it's a fairly simpler question. So the next question is a similar problem, but instead of discharge temperature, here we have to find out the work done during compression process. So same inlet temperature of 20 degrees Celsius and 1 bar, and same process. This is PV raised to power 1.2, and your discharge temperature is 10 bar. So your work, if you integrate VdP, so you will get this relation. So here you substitute that in terms of pressure and integrate that, so you will get this relation. So mRT1 into n by n minus 1 into your pressure ratio raised to power n minus 1 by n minus 1. So here n is 1.2, so we are substituting that R, so per kg, so we substitute 1 into R is given 0.287. Your inlet temperature is known, so 293 into n value substituting in, so and pressure ratio is substituting, we will get 236.13 kilojoule per kg of air. So this is the work done for compressing it from 1 bar to 10 bar. Next question is, a multi-stage compression incorporates 3 number of stages with perfect intercooling between the stages. The compressor receives air at pressure 1 bar and delivers the compressed air at pressure 8 bar. For a minimum indicated power requirement, the pressure ratio for each stage is dash. So now previously we saw 2 stages. So here similarly we have a inlet suction pressure of 1 bar, and the discharge pressure you require is 8 bar. Now what they are saying is, with perfect intercooling, and you require 3 number of stages. So number of stages 3. So there we saw your intermediate pressure is root of P1 P into P2 raised to power 1 by 2. So here what will happen is your pressure ratio between any 2 stage will be your discharge pressure divided by suction pressure raised to power 1 by n. N will be your number of stages. So here it will be 8 raised to power 1 by 3. So it will be 2 bar. So the pressure ratio for between each stage will be 2 bar. So if you see, the same relation will hold for the previous equation also. So there it was 16 and 4 bar. So if you substitute there, you will get 16 by 4 will be 4 raised to power 1 by 2, which is 2. So the intermediate pressure will be ratio will be intermediate by P suction into 2 is equals to 2. So 2 into 4 8. So that's what we got previously also. So you can use the same relation, this relation for that also. This will hold good for all intermediate pressures calculations. So here we have given 3 number of stages, so we will substitute n equals to 3, 8 raised to power 1 by 3, which is 2 bar. So answer is B. So next we will see some, I hope till now there is no doubt and we are clear with this. Okay, so we will move on to solve some numericals. So we have a 1 meter cube of gas which is compressed adiabatically from 1 bar to 5 bar in a reciprocating compressor with 8% clearance. So clearance volume is given 8%, if the exponent of the re-expansion curve is 1.1 instead of 1.4, find the percentage increase in the work of compression. So a schematic representation is shown here. So this is your reciprocating compressor, the piston arrangement, and you have a delivery valve and suction valve here, and this is the process which it takes. So 4 to 1 is your suction, where the fluid comes in, and then 1 to 2 is where your fluid get compressed. Then 2 to 3 is your exhaust, and 3 to 4 is again expansion of the fluid inside. So here 1 to 2, which follows a adiabatic process where gamma is 1.5, and 3 to 4 the expansion is 1.1. So that's what is given. So we'll see how to solve this problem. So initially adiabatic compression expansion, because we need to find out the percentage change in work of compression. So initially we'll assume both of them are adiabatic process. So for that adiabatic compression expansion, your work you can express it as gamma by gamma minus 1 P1 into V1, or suction pressure, suction volume, into pressure ratio raised by gamma minus 1 by gamma minus 1. This is gamma. So and then substituting gamma as 1.4, we know the inlet pressure P1 as 1 bar and P2 as 5 bar, and your suction volume is 1 meter cube. So substituting that, we'll get total work done as 20405 50 Newton meter. So this is the initial work done. Then adiabatic compression and polytropic expansion. Here we can find out volume 4. So V3 and V4 is an polytropic process with gamma equals to 1. So V3, if you see, that is the clearance volume. So the clearance volume is given as 8%. So 8% is 0.08 times of your V1. So your V3 by V4 will be equals to P2 by P2 and P3 will be same pressure, and P1 and P4 will be same pressure. So P2 by P1, which is 5 by 1 raised to power 1 by 1.1. So V4 we can find out, which will come out to be 0.3456 meter cube. So V1 will be this is 0.08 into V1. V1 is 1 meter cube, so this is 0.08. So sorry, swept volume. Swept volume is 1 meter cube. So V1 will be V4 plus 1 meter cube swept volume. So 0.3456, which is V4 plus swept volume 1 meter cube, will equal to 1.3456 meter cube. So we know all the volumes here, the volumes which we require, V1, V4 and V3. This work done which we have calculated is the difference in work. If you see the process, the W, here we have Vs. If you see for process 1, 2, it will be gamma by gamma minus 1 P1 V1 into P2, the same bracket equation. And for process 3, 4, you can write it as gamma by gamma minus 1 and P4 V4 into the expression in the bracket. So if you see V4, that you have to take a difference. So if you take a difference, what you will get is the swept volume, V1 minus V4. V1 minus V4 is the swept volume Vs. So this W directly gives you the difference in work done for the compression and expansion process. So similarly, if you see for the difference in work, the total work done which is done, so n by n minus 1 P1 V1 by P2 by P1 raised to power n minus 1 by n. For this is for the compression, and similarly for expansion. Here the initial process is adiabatic, so N will be 1.4 and here M will be 1.1. So on substitution we get the work as 218,870 Newton meter. So we have found out the two work done, so we can find out the increase in work. So increase in work is the difference in work divided by the initial work, so it will be 7.26%. So that's a 7.26% increase in work when you have an polytropic expansion process. So the next one is an R22 hermetic reciprocating compressor with 4% clearance is to be designed for a 7.5 ton capacity of 4 degrees Celsius evaporating and 40 degrees Celsius condensing temperature. So your what here is given is a compressor which clearance volume is 4%, which is designed for a 7.5 ton capacity refrigerator, which evaporating temperature is 4 degrees Celsius and condensing temperature is 40 degrees Celsius. The compression index may be taken as 1.15. The number of cylinders may be selected as 2, and the mean piston speed of piston is 3 meters per second approximately. The stroke to bore ratio for fluorocarbons may be taken as 0.8. Your pressure drop at suction and discharge valves may be assumed to as 0.4, 0.2 and 0.4 bar respectively. So determine power consumption of the compressor and COP of the cycle, volumetric efficiency of the compressor, bore and stroke of the compressor. So motor speed is given as 1400 rpm. If the evaporator temperature drops to minus 2 degrees Celsius with the condenser temperature and other condition remain same, what will be the capacity and power consumption of this compressor and COP of the system? So this I have previously we saw some vapor compression cycle, so it's a clubbed question of compressor for the VCR problem. So we'll see how to solve this. So if you see, this is the process. You have a condenser, this is at 40 degrees Celsius, and you have a compressor and evaporator. This evaporator is at 4 degrees Celsius and that is compressing, and you are passing it to condenser where it is cooled and you will have a saturated liquid which is going to expansion device and will come out and it will go to evaporator. So if you see, the above side between expansion and compressor is a high pressure side and below it's a low pressure side. So that process is shown in a pH diagram, a similar process. So 1 to is here we are assuming everything in ideal. So 1 to 2 is an isentropic process, and 2 to 3 your constant pressure, and 3 to 4 and 4 to 1. But here you have specific pressure losses which is reported. So here they have said that suction and discharge valves, there's a 0.2 and 0.4 bar pressure drop. So for correspondingly for 4 degrees and 40 degrees for R22 mixture, this is R22 refrigerant, we'll find out that your pressure is 5.657 and 15.335 bar. Your suction pressure, there is a pressure drop of 0.2, so 5.657 minus 0.2, which will be 5.457. So that is the suction pressure where in the compressor, and you after compressor there is a pressure loss of 0.4. So your compressor should compress it more. So 15.335 plus 0.4, so that will come out to be 15.735 bar. So this is your suction and discharge pressure of the compressors. So now if you see the enthalpy of suction of vapor, that is inlet to the compressor H1, which is at 4 degrees saturated vapor, will be 406.8. You can take this directly from the pH curve. So saturated vapor H1 will be is 406.8, and specific volume of vapor is 0.0431 meter cube per kg. So now, enthalpy of liquid H3 will be equal to H4. It's an isenthalpic process across the valve. So your H4 will be 249.1. So from this we can find out the specific refrigerating effect, which is H1 minus H4 will come out to be 157.7 kilojoule per kg. So we'll see we have found out the specific refrigerating effect. So we'll also find out specific work done. So the specific work done here, we have given that gamma is 1.15. So if we assume it to be in isentropic process, we will go can directly find it in the chart across the S1 equals to S2 entropy line, constant entropy line. But in the problem it's stated that your compression index is 1.15. So similarly we will substitute in the equation. So gamma by gamma minus 1 or n by n minus 1 into P1 V1 and your pressure ratio, similar expression which we are using. So on substituting we will get that a specific work is 26.6 kilojoule per kg. So now we can find out the mass flow rate. So the problem, it is given that it is designed for a 7.5 ton refrigerator. So 7.5 into 1 ton is 3.52. Can use 3.52. Here it's given 3.5167. So 3.52 kilowatt. So 7.5 into 3.552 divided by, you have already found out the refrigerating effect. So this will be equal to m dot into q naught, the refrigerating effect. So say m dot will be your 7.5 into 3.52, the capacity of the refrigerator, divided by your specific refrigerating effect. This will come out to be 0.1673 kg per second. So now we have found out the mass flow rate. Now we can find out the work done on the compressor. So work done is your specific work into mass flow rate, which will come out to be 4.45 kilowatt. So now we know both your capacity and work done. So we can find out COP. COP is your useful effect by energy spent. So useful effect is nothing but the refrigerating capacity. So you can use m dot into q naught, or you can use m dot will cancel out. So you can use directly a specific refrigerating effect divided by specific work. So specific refrigerating effect is 157.7 and specific work is 26.6. So your COP is 5.9. So this, the first part of the problem is done. So now next is to find out volumetric efficiency and bore and stroke of the compressor. So now volumetric efficiency is defined as 1 plus C, your suction pressure, by PS by P1, and minus C PD by P1 raised to power 1 by N. So this relation given, but we can directly use 1 plus C into RP raised to power gamma 1 by gamma minus C RP raised to power 1 by gamma. So here it's taken into account because of the pressure losses. This expression is given. This is slightly complicated, so we can neglect this. So see, this is not part of the course, but anyway. So 1 plus C PS by P1 raised to power 1 by N minus C PD by P1 raised to power 1 by N, and R is the compression ratio. So on substituting, we will get that volumetric efficiency is 0.8585. So majorly the problem we will get is the normal relation between the suction and discharge pressure. So, okay, so piston displacement per cylinder will be, you have volumetric efficiency. So volumetric efficiency is your swept volume of the fluid divided by your swept volume. So swept volume is VE dot P, and this is equals to m dot by 2 because you have two cylinders. That's what is given in the problem. So yeah, the number of cylinders may be selected as 2. So you have two cylinders. So it's m dot by 2 into for converting into volume, you multiply by specific volume, divide by efficiency. So this will give me the swept volume. So that is equals to 0.252 meter cube per minute. Now this is equal to pi d square by 4 into L. This is just the volume of the cylinder, into N is number of rotation, or we can express in terms of speed. So 30 into cm by L. So your mean speed is given is 3 meters per second. So on substituting that, we can find out your diameter, and diameter and length ratio is also given. Bore and stroke. Now length gets cancelled, so you can find out directly diameter. So it will come out to be 0.06 meter, and length is, I think it's given. Yeah, the stroke to bore ratio is 0.8. So length is 0.8 into diameter, so it will come out to be 0.048 meter. So from there we can find out the speed. So it will come out to be 1875 rpm. So next part of the question was to find out if evaporative temperature goes to minus 2 degrees Celsius. So similarly, we have found out your suction pressure with minus 0.2 bar reduction pressure drop, and H1 and V1, and similarly specific refrigerating effect, and your work done. So that is 32. So and similarly volumetric efficiency. So now we know your volume, you know this volume of the cylinder, or swept volume. So using that 2 into, because twice of the cylinder, 2 number of cylinders into swept volume into volumetric efficiency. So this will give me volume divided by specific volume. So this will give me your mass flow rate, which is 0.1312 kg per second. So now we know the new mass flow rate. So we can find out the capacity, total capacity is mass flow rate into specific refrigerating effect of the new one, which is 20.4 kilowatt, and power consumption is similarly mass flow rate, the new mass flow rate, into specific work done, 32, which is 4.2, and similarly COP we can find out, which is 4.86. So if you see, previously the COP was 5.9, so and it will go down. If you, because temperature gaps increases, your COP will also go down, and also this happens because your specific volume will also go down. Your suction, because at minus 2 your pressure will go down, your specific volume will go down, so your volumetric efficiency goes down, and so you will have more, you have to do more work, but you are compressing very less fluid, and capacity, everything will go down. That's what is explained in the note. The next problem is a catalog data for a 6-cylinder refrigerant R22 compressor operating at 29 revolutions per second indicate a refrigerating capacity of 96.4 kilowatt and a power requirement of 28.9 kilowatt at an evaporating temperature of 5 degrees Celsius and a condensing temperature of 50 degrees Celsius. The performance data are based on 3 degrees Celsius liquid subcooling and 8 degrees Celsius superheating of the suction gas entering the compressor. So the cylinder bore is given 67 millimeter, and piston stroke is 57 mm. Compute clearance volume, volumetric efficiency if clearance volume is 4.8%, and actual volumetric efficiency and compressor efficiency. So now similarly we can find out all the datas for for 5 degrees Celsius and 50 degrees Celsius. So the enthalpies are all listed. So your enthalpy is at inlet of the compressor. H is 413.1 and specific volume is given, and entropy is given. So after that, if you follow an isentropic process, when you reach 50 degrees Celsius, the pressure is 1942 kilopascal, corresponding to 50 degrees Celsius. The property of refrigerant will be H is 444.5 and corresponding specific volume. So the enthalpy of liquid leaving the condenser and entering the evaporator is also known, with assuming 3 degrees liquid subcooling. It says 47 degrees Celsius, your enthalpy is 259.1. So we know all the enthalpies and specific volume at each point. So now the clearance volume efficiency is so here what we know is 4.8% is the clearance volume. So 100 efficiency, this is written in terms of volume. So 100 minus 4.8 Rp raised to power 1 by gamma, you can write it in terms of volume. So volume will be V1 by V2. So initially at point 1 specific volume is 43.2, and after compression your specific volume is 14.13. So substituting that 43.2 is V1 by V2. You see, you write it as Rp raised to power 1 by gamma. Here you are writing in terms of volume. So 43.2 divided by 14.13 minus 1. So this will come out to be 90.1 or 0.9. So 90% volumetric efficiency. So this is using the volumetric efficiency relation. So now the compressor displacement area will calculate. So we know it's a 6-cylinder compressor and it's running at 29 revolutions per second, and your compressor is pi by 4 d square into L, stroke volume and bore diameter is given. So this will come out to be 0.03497 or 34.97 liters per second. So the actual rate of refrigerant flow is, so here the refrigerant capacity is given as 96.4 kilowatt. So 96.4 kilowatt divided by your refrigerating effect, so H1 minus H3 or H4, so that will come out to be 0.626. So this is the actual mass flow rate. So this into now converting it in terms of volume, you multiply with the specific volume. So suction specific volume is 43.2. So mass into specific volume will give me volume, that is 27.04. So now we know the specific volume, the volume of fluid which is entering, and the swept volume is also known. So the actual volumetric efficiency is 27.04 divided by swept volume, which is 34.97, into 100 will come out to be 77.3%. So next question is, the compression efficiency is the isentropic in the isentropic work of compression. What is the compression efficiency? Okay. So for that we will find out the difference between the compressor enthalpies, V444 minus 413.1. So that's give me a specific power requirement is given as 28.9 kilowatt. So we know actual power, and the required power is ideal power is isentropic power is 444.5 minus 413.1 into mass flow rate. Here they are divided by actual work by mass flow rate. So you will have specific actual work, which is 46.2. So that divided by specific work equals to 68%. So the compression efficiency is 68%. That is ideal by actual. So actual is 28.9. Ideal is your 444.5 minus 413.1 into 0.626. So that will give me the compressor efficiency which is 68%. I hope this is clear. So moving on, we have a single cylinder, single acting reciprocating air compressor which has a cylinder of 24 centimeter diameter and a linear piston speed of 100 meters per minute. It takes in air at 100 kilopascal and delivers at 1 megapascal. Determine the indicated power of the compressor. Assume the law of compression to be PV raised to power 1.25 and the temperature of air at inlet is 288 Kelvin. It's a negative clearance effect. So if you see, this is the process. We are assuming that there is no clearance. So 1 to 2 and then coming back, it will all be same. So you are starting at 0, then taking in fluid and compressing it and then discharging, and it goes to 0 because there is no clearance volume. So what will happen is here your inlet pressure is 100 kilopascal and your exit pressure is 1 megapascal, which is 1000 kilopascal. So now the pressure ratio is P2 by P1, so that will come out to be 10. Then swept volume is pi by 4 d square L into number of rotations. So we know pi by 4 into d is given as 24 centimeter. 24 by 100 raised to power 2 into linear piston speed is given. So we can multiply directly L into RPM. We can multiply directly by piston speed. So 100 divided by 2. So because piston speed equals 2 into L into N. Swept volume, stroke length by into speed or speed of rotation. So 2 into L into N will be equals to piston speed. So we can directly substitute L into N by 100 by 2. So substituting that, we can find out swept volume, which will come out to be 2.261 meter cube per minute. So now we can find out the work done. So for work done is P1 V1 into N by N minus 1, similar equation. So on substituting pressure, inlet pressure at 100 kPa, this is 100 into kPa kilopascal, so into 10 power 3 into volume V1, which we have calculated as swept volume. So this will be equal because there is no clearance volume. So V1 will be the swept volume. So 2.261 divided by 60 into N by N minus 1. N is 1.25. On substituting, we will find out that work is 11,030 watt or 11.03 kilowatt. So then the indicated power of the compressor is 11.03 kilowatt. So the next question is, a single acting single stage air compressor developing indicated power of 11 kilowatts runs at 200 rpm and has a linear piston speed of 100 meters per minute. If the suction pressure and temperature are 100 kilopascal and 15 degrees Celsius respectively, and the delivery pressure is 1000 kilopascal, calculate the dimension of the compressor cylinder. Assume the law of compression is to be PV raised to power 1.25 equals constant. Neglect clearance effects. So here previously we were asked to find out the indicated power. Here they have directly given indicated power as 11 kilowatt, and rotation speed is given 200 rpm, and piston speed is also given 100 meters per minute. So similar pressures 100 and 1000 kilopascals. So here we have to find out the dimension of the compressor cylinder. So we know V1 by V2, which will be equal to P2 by P1, equals to 6.31, or the pressure ratio raised to power 1 by n, 6.31, and work done per cycle is P2 V2 plus few. If you multiply, this will come out to be n by n minus 1 into P2 V2 minus P1 V1. It's just expanded equation. If you multiply it, if you see n into P1 V1, it will be minus of minus 1 will get cancelled out, so it will be n P1 V1, and similarly n P2 V2. So it will be n P2 V2 minus P1 V1 by n minus 1. So the similar equation which we saw previously is just, it's an expanded form. So the mean effective pressure will be the work done per cylinder, work done by the displacement volume. So substituting the work done and divide by swept volume, we can displacement volume is swept volume is V1. So substituting V1, we can find out that the effective pressure is 292.4 kilopascal. So now piston stroke is piston speed per minute by piston strokes per minute. So the same equation, 2L into N equals your speed of the piston. So you can find out the stroke from that expression. It will come out to be 0.25 meter or 25 centimeter. Now next is indicated power. Indicated power is mean effective pressure into stroke length into area of the cylinder into number of rotations, n. So on substitute, we know indicated power is 11 kilowatt, which will be equal to mean effective pressure into stroke length, which I have calculated 25 centimeter, 0.25, into area is pi by 4 d square. So substituting that into number of cycles, which is 200 by 60. So from there we can find out the diameter. So diameter will come out to be 23.98 centimeter. So the next problem is, it is desired to compress 16 meter cube of air per minute from 1 bar, which is 100 kilopascal, and 294 Kelvin to 10.5 bar. So we know the volume of air to be compressed 60 meter cube and per minute, and your suction pressure is 1 bar and your discharge pressure is 10.5 bar. The minimum power required to drive the compressor with two-stage compression and compare it with power required for single stage compression. The next question is the maximum temperature in two cases, the heat to be removed in the intercooler per minute, and the amount of cooling water required per minute if the inlet and outlet temperatures of to and fro from the intercooler are 15 degrees Celsius and 40 degrees Celsius. Assume the value of induction of compression process is 1.35. So we'll see how to solve this. So we are basically comparing two processes. So one is a two-stage process, you're compressing and then intercooling and compressing again, and there is a single stage compression. So we know the suction and discharge pressure, which is 1 bar and 10.5 bar. So your pressure ratio is 10.5. So if you are doing a two-stage compression, then your intermediate pressure is root of P1 P3, which will come out to be 3.241 bar. So now the pressure ratio between two stages is any two stages 3.241. So from there we can find out the work done. So for a two-stage process is 2 into work done in single stage n into n minus 1 into P1 V1. uh, rp raised to power n minus 1 minus 1. So substituting n value and p1 and v1 is it's given 16 meter cube per minute, so 16 by 60. So substituting that, we'll find out that your work done is 73,000 or 73.17 kilowatt. Now similarly, if this process is done in a single stage, then your pressure ratio is 10.5. On substituting that, we'll find out your pressure for a single stage, the work done is 86.25 kilowatt. Now similarly, for a two-stage process, P3 by T1 equals P3 by P1 raised to power n minus 1 by n. So your pressure at temperature at 3 will be similar, because T2 after intercooling your 2 will be equals to 1. So on substituting that, we can find out your pressure. So first we'll assume find for a single stage process. So T3 by T1 equals to P3 by P1. So P3 by P1 is 10.5. So your T3 will be 541 Kelvin or 268 degrees Celsius. So similarly, for a two-stage process, your T2 will be T1 into P2 by P1 raised to power n minus 1 by n. This will come out to be 398.72 Kelvin or 125.72 degrees Celsius. So if you see, we have brought down the temperature more than 140 degrees Celsius by intercooling. So the next is to find the mass of air compressed. So M is P1 V1 by RT1. So we know P1 1 into 10 power 5 into V1 16 meter cube per minute divided by 287 into 294, which is temperature, which will come out to be 18.96 kg per minute. So now heat rejected by air to the intercooler water per minute is m dot into Cp, or Cp of air, T2 dash minus T2. So 398.72 minus 294, and mass is already calculated, so it will come out to be 1995 kilojoule per minute. So similarly, heat gained by water in the intercooler per minute is m dot into 4.187 into the temperature difference of the water, which is 40 minus 115, so which will come out to be 19.06 kg per minute. Sorry, this will be equals to your heat rejected by the air. So from there we can find out the mass of water, cooling water required, which will come out to be 19.06 kg per minute. So the next question is, we have a two-stage single acting air compressor for a diesel engine which runs at 250 rpm and takes in 6 meter cube of air per minute at a pressure of 1 bar and temperature of 15 degrees Celsius. This delivers the air at 70 bar, and compression is carried out in each cylinder according to the law PV raised to power 1.3 equals to constant. Assuming complete intercooling and mechanical efficiency of 80%, determine the minimum power required to drive the compressor. Calculate also the cylinder diameter and common stroke if the average piston speed is 170 meters per minute. So we have a single acting two-stage compressor, so which is this RPM is 250 RPM, and your mass of your volume of air taken is 6 meter cube per minute. Your suction pressure is 1 bar, and your suction temperature is 15 degrees Celsius. Your discharge pressure is 70 bar, and compression is carried out PV raised to power 1.3, and they are saying their complete intercooling and mechanical efficiency of 80%. So we need to find out minimum power required to drive the compressor. So also we have to find out diameter and stroke if the piston speed is 170 meters per minute. So we can find out this assuming perfect intercooling. So we can find out the indicated power, which is 2 times the work per stage. So we can find out directly substituting rp raised to power 1 by 2 gamma. So because stage will be root of p1 into p3. So we are directly writing in terms of p1 and p3. So substituting that, we'll find out your work done is 54.773 kilowatt. So if we assume we have given that mechanical efficiency is 0.8, then the power required is 54.773 divided by 0.8, which will come out to be 68.466 kilowatt. So minimum brake power required to drive the compressor is 68.466 kilowatt. So next is we know stroke. You need to find out stroke. So mean piston speed is 2 into stroke into stroke into speed of rotation. So the mean piston speed is 170 meter per minute divided by 2 into 250 rpm. So this will come out to be 34 centimeter or 0.34 meter. So if you see a low pressure cylinder, the stroke volume in the low pressure cylinder is V1 equals 6 by 250, 6 meter cube per minute divided by rpm. It will come out to be a pi by 4 d square into L. So we have already calculated length. On substituting, we can find out diameter of the low pressure cylinder to be will come out to be 0.0899. So the diameter of the low pressure cylinder is 0.3 or 30 centimeter. So if there is a perfect intercooling, then P1 V1 equals to P2 V2. Then V1 is directly proportional to D square. So P1 into D square, D1 square equals to P2 into D2 square, because stroke length will remain same. So D2 by D1 equals D2 by D1 raised to power 2 equals P1 by P2. P2 is nothing but a root of P1 P3, the intermediate pressure. So this is root of 1 by 70, which will come out to be 0.1196. So D2 by D1 will come out to be 0.346, or the high pressure cylinder diameter will be 0.346 times D1, which will come out to be 0.1038 meter or 10.38 centimeter. So that's all for today. These are the problems on compressors. Thank you and all the best for your exams.